In the 1950s, the United States tried to build an airplane that could remain in the sky for days at a time, without constantly stopping for fuel. The solution sounded almost impossible. Put a nuclear reactor inside an airplane. And this wasn't just an idea on paper. A working nuclear reactor actually flew aboard an American aircraft dozens of times. On the ground, engineers successfully used nuclear heat with modified jet engines. For a brief moment, a nuclear-powered airplane seemed technically possible. Then, in 1961, the entire program disappeared. So what happened? Why did America spend years developing nuclear aviation, prove that some of its most important components could work, and then abandon the idea? The answer begins with one of aviation's oldest problems. Fuel has weight. If you want an airplane to fly farther, you normally give it more fuel. But that additional fuel makes the aircraft heavier. A heavier aircraft needs more lift, more structure, and more power. And all of that can require even more fuel. For ordinary aircraft, this is manageable. But during the early Cold War, the United States wanted something extraordinary. Strategic aircraft capable of remaining airborne for extremely long missions without constantly depending on tankers or distant air bases. Nuclear energy offered a completely different possibility. A reactor can produce enormous amounts of heat from a relatively small amount of nuclear fuel. Instead of endurance measured in hours, engineers began imagining endurance measured in days. Formal American research into nuclear aircraft propulsion began in 1946. By the early 1950s, the effort had grown into the Aircraft Nuclear Propulsion Program. Major aerospace and engineering companies became involved, including General Electric, Pratt & Whitney, Convair, and Lockheed. And the basic idea wasn't as mysterious as it sounds. A jet engine takes in air, compresses it, heats it, and accelerates hot gas through the engine to produce thrust. Normally, burning fuel provides that heat. Engineers wondered whether a nuclear reactor could provide it instead. The reactor wasn't supposed to generate electricity for an electric motor. It would become the heat source for the jet engine itself. In theory, that could dramatically reduce the aircraft's dependence on conventional fuel. But nuclear power replaced the fuel problem with a much more dangerous engineering problem: radiation. A reactor on the ground can be surrounded by enormous amounts of shielding. An airplane doesn't have that luxury. Every kilogram of shielding has to fly. More shielding protects the crew, but increases weight. More weight requires a larger aircraft. A larger aircraft requires more structure and more powerful systems. The solution was beginning to create another version of the problem it was supposed to solve. The Air Force needed real data. So engineers modified one of the largest aircraft ever built, the Convair B-36. The experimental aircraft became known as the NB-36H. Inside, it was an operating nuclear reactor. But there is an important distinction. The reactor did not power the aircraft. The NB-36H still relied on its conventional engines for flight. The reactor was carried primarily to determine whether a nuclear reactor could operate aboard an aircraft while the crew remained protected. Between 1955 and 1957, the NB-36H completed 47 test flights with the reactor aboard. That alone was remarkable. A functioning nuclear reactor was literally being carried through the sky. The crew compartment received extensive shielding, including heavy materials designed to reduce radiation exposure. But the aircraft also demonstrated exactly why the concept was so difficult. Shielding was incredibly heavy, and the reactor was only one part of the problem. Engineers still needed a practical propulsion system. General Electric pursued what became one of the most important experiments of the entire program. At a remote test site in Idaho, engineers built enormous experimental systems, known as the Heat Transfer Reactor Experiments. Modified General Electric J-47 turbojets were connected to nuclear heat sources, and the concept worked. The reactor could provide heat that allowed the jet engine system to operate. This was an extraordinary engineering achievement. By this point, America had flown an operating reactor aboard an aircraft and had demonstrated nuclear-heated jet engine technology on the ground. But combining those achievements into one practical airplane was far harder. The complete system needed a reactor, shielding, engines, controls, structural reinforcement, and protection for the crew. And then there was another problem that couldn't be solved simply by making the aircraft larger. What happens if it crashes? A conventional aircraft accident is already dangerous. An aircraft carrying an operating nuclear reactor introduces an entirely different set of consequences. Engineers had to think not only about normal operatia,